I will start then. Okay. So, many thanks for being invited to present here. Hopefully, the material will be of some interest at least. I guess it's had a big build-up now with all the technical glitches. Hopefully it doesn't disappoint. So what I'm just going to briefly really cover, because it's a very deep and wide subject area, of course, is really the role of robust design techniques, essentially dealing with the effects of uncertainty variation, play within the broader sort of design and process, decision-making process, if you will, and in particular how it can help us gain trust in the models we use to make design decisions. So again, I'll skip this next slide very, very quickly. It's the obligatory "Who are Rolls-Royce" slide. What I'll then just jump into is, again, a sort of a brief definition of what we mean by when we say verification and validation. And then, obviously, to put it in a particular context, I've chosen gas turbines as sort of an example of the issues, the challenges that we might face. And then, again, just briefly, what I've really classified the sort of two approaches to building and using models, different types of situation, sort of the reverse engineering situation, where we're using statistical techniques to analyze data to understand what has happened in the real world, and then the forward engineering, which is obviously developing predictive models to help us with the actual design process. And then, just as a finish off, actually, since we'll be talking about how do we develop trust in our modeling techniques, just a little example of, well, do we actually trust maths at all? Okay. So, again, I'm not going to go through this slide in detail. It's here because we're essentially obliged to mention who we are at Rolls-Royce. The key point is we don't make cars. So, for any of you thinking that in the question and answer session you might ask for a discount, I'm afraid I can't oblige. We're just a big multinational company. Power is our business, really. Aerospace, civil and defence, and marine and nuclear power as well, in fact. So, anyway, moving swiftly on. So, what do we mean by verification and validation? So the definition is taken, as it shows here, from Barry Bowen, Software Engineering Economics in 1981, where he defined validation as being able to answer the question, are you building the right thing? And verification as, are you building it right? So setting aside the poor English there, it's about really understanding how have we understood the customer requirements and therefore defined a correct specification. That's the validation part. And then, of course, given that specification, is the solution we develop correctly implemented? In other words, does it deliver to those customers? If we think about mathematical modeling simulation techniques, then there's actually two contexts here. When we're actually applying them as part of the design process, then they're very much part of the verification stage, because we're trying to, well, they're involved in the verification stage because we're trying to make predictions and we have to confirm those. But when we develop the models in their own right, well, they have their own verification and validation too. Are we developing the right model? Have we developed it right, to use the same phrasing? Yeah. So it's as much the latter part that I'm going to be looking at in this presentation. When we develop these models, how do we gain that trust in them so when we use them, we can believe what they're telling us? Okay. So if you think about a gas turbine, well, again, obviously it doesn't look like a box on here. It's obviously a very complex piece. The whole point here is this is a P diagram that's going to develop on the screen. So there are purposes to which we design the gas turbine. It's supposed to do particular jobs. So example, main purpose of the gas turbine is to generate thrust, but it also happens, in most occasions at least, to provide a source of cabin air, pressurised cabin air for the aircraft. So that's what it's supposed to do. The most of the design process actually tends to be dealing with what we wouldn't like it to do. So it's a particular technology. It has its own, as we describe here, side effects. So we generate noise, waste heat, vibration. We pass loads back into the airframe. It's a combustion process, so there are obviously combustion byproducts and therefore emissions that we have to deal with. So there are the consequences of operating the system that we have to account for as well. We also have to consider, shall we say, the usage and the environment within which it's going to operate. These influence our design choices at the end of the day, but also these are many of the sources of uncertainty in the analysis. So we will make key assumptions about certain things, particularly in terms of when we define characteristics of the gas turbine. We know in the real world they'll be subject to variation due to, say, manufacturing and assembly. But as I've said, also operating conditions are uncertain, as are mission profiles, deterioration rates, etc., etc., etc. So again, we have to ultimately, this is part of robust design, identify those sources of variation, account for them properly, and answer that question: can the design cope? More complication, of course, is that, of course, this isn't a sort of a static operation. We don't just turn a gas turbine on and just leave it running. There's an interaction with the pilot, so there's different demands for different levels of thrust throughout its operation. So we have signal factors to account for. So are they noisy as well, is another question that we need to answer, and how do we cope with the noisy signal but behave in the expected manner? And then finally, we have to answer all of these, or deal with all of these issues simply by choosing the right set of our control factors. So the right size, the right shape, the right choice of materials. If all of those are decided on in the proper way, then hopefully we end up with a product that does what it says it does, to the right level and the right level of consistency, and also has properly managed set of side effects. Okay. So again, just to reiterate that, the key thing here is that all of those behaviours span a broad set of physics. So the whole design process involves typically these days a very large number of very different disciplines and simulation tools. When we get to safety, though, there's still the issue of can we trust the models completely? Well, typically we have to at least do what we call confirming tests to demonstrate compliance to regulation. So we can't wholly sit in the virtual world. And of course, as time has gone on, these models themselves have become more and more sophisticated, more and more high fidelity, but unfortunately more and more time consuming to create and run. So if we can only rely on those, that actually slows down the design process. So we often end up, shall we say, putting a layer on top of those of more abstract mathematical models, sometimes we refer to these as surrogate models, which we can then use as essentially a lower fidelity version, but something that's responsive enough to make decisions in a timely manner. So it's a very sort of multi-layered, multifaceted process that we have to deal with. So if we think about the sort of the reverse engineering side of things, essentially, we'll have a situation where we're gathering real-world data. Perhaps an event happens, or there's an issue where we see behaviours not quite where we expect them to be. We need to understand what's going on and ultimately get down to root cause. So this is what I'm talking about by data analysis, to explain what's happened. And of course, it's a fairly well-established process, very statistical based. The first step is obviously to collect the available data. In this case, I'm using special courses in a very similar way to you might do in production engineering and manufacturing. It's something that is a classification, an event that either happens for a period or distinguishes one subgroup to another, which means that the means, behaviours, or the variations in behaviours across those subgroups is different. So we need to understand what are those possible special causes. They need to be logged as part of the data, so that adds to the level of complexity, because otherwise without that we won't be able to do this very crucial stage in the analysis. So that's really about picking out, well, there's an unusual subset of data here. Maybe one operator is different to the others, or maybe one route causes a difference in behaviour to another. There will hopefully be something that we can identify as different, perhaps unique. The next question then is, well, why is that happening? So you dig down into the next level down. Ultimately, you start looking for correlations. Is there a pattern here that we can identify between the available data sets, which again helps us explain more and more close to the root cause what's going on. Ultimately, we want to turn that into at least perhaps a local model, but something which again we can look at and understand. So obviously what we've got here is just a typical sort of contour plot of a model, two factors against one response. The key to the other part of three charts around it are, well, this is the verification part of that model. So we've built a mathematical model. In fact, actually, it's a bit of verification and validation. So does it conform? Is the right model to have built? Well, we need to understand how well it fits to the mathematical modeling technique. So do the residuals fit appropriately? Say, do they behave themselves? Are they biased or not? Validation is then much more on, well, if we give this model a set of conditions that weren't involved in developing it, how good is it predicting those outcomes? So again, there's a verification and validation phase before we actively use that model. Okay. So these well-established techniques, very useful, of course, in the real world, but of course, it's not necessarily great for the design process. First obvious reason why is because of this thing highlighted as a lag. You only can develop such models after the fact, perhaps very long after the fact. So it's not so great if you have to wait for your customers to identify issues or show that there's poor performance, and they have to suffer through that for a while before you start figuring out what's going on and dealing with it. So lag is obviously an issue. The applicability, again, is another one, because, again, they'll typically be local to a particular design or an implementation. So making broad-ranging predictions about larger design changes may not be appropriate. And, again, there is an issue with, as I've called it here, aliasing. So you can only fit the model to data you have available. If in fact there is something you hadn't measured and recorded as you should have, which is the real root cause, and that happens to be correlated to what things you did measure, well, you can jump to the wrong conclusion. Again, this part of the validation might be, shall we say, putting your engineering hat on and say, does this actually make sense that this parameter is driving this behavior? But if the answer is no, well, there may be very little you can do about it. So there's a lot of good that can, of course, come from these things, but we do have to be careful, and we have to be rigorous about that validation and verification process to be able to say, well, these models tell us the truth, and therefore we can decide and act appropriately. If we look at the other typical scenarios, so this is what I've called the forwards engineering, as I said before. So this is again where we typically draw upon large simulations or other mathematical models to help us make design decisions before the fact. Again, we have to recognise that, of course, it's not possible to do a one-to-one comparison, although it's always tempting to. We build the perfect simulation model, and then we run an engine, and the answers are the same. well, it must be the fault of the model, so we tweak the tuning parameters until they match perfectly. Of course, that's not the appropriate thing to do. What we have to recognise, we live in a stochastic world, we live in inherent variability, and therefore what we should aim to do is say, does the model present the same population behaviours as the real world? So we want a sample of model outcomes and a sample of real world outcomes and compare those characteristics. And to do that, of course, you need a stochastic framework around your modelling techniques to help you develop or synthesize, if you will, those samples. So this is that process. Again, I guess you're all familiar with this because it's essentially robust design in action. You know, you obviously need to start off with understanding what your performance characteristics are, what the customer requirements are, and from a robust design standpoint, what are the ranges of tolerable variability that the customer will allow. Then it's a natural process of understanding, well, what are the key design characteristics that will influence design behaviours. Through your normal modelling techniques, that gets you to the first step. Perhaps through optimization, you end up with the right combination of your design parameters that achieve the required target performance. Then, of course, it's about understanding what causes variation in the system and modelling that appropriately, and then using the appropriate uncertainty quantification techniques to propagate the uncertainty through the system to develop the prediction of, well, this is how the performance varies. Then, of course, based on a sort of balance of what the customer will allow in terms of deviation from the specifications and what the business can cope with in terms of the cost of making you more or less compliant, you have to decide whether you're happy with this kind of picture. So is the level of conformance to the specification acceptable? Yeah. Basic premise of it. So this is fine, but of course it has its own issues. The main one basically that it relies on a set of key assumptions. First one being that the model we're using for predicting performance is a good model. So in other words, we have to have done the verification and validation on the model itself, even from a deterministic point of view. Similarly, the included uncertainty, the way we've modelled that, the distributions we've chosen, the quality of the data perhaps that we use to develop those models and implement them, are they correct and accurate? Because they will change the answer. Again, the uncertainty quantification techniques, do we use a Monte Carlo or a mean value method or some other technique? What are the implications of one of the others in terms of precision and accuracy of their estimates? And also, of course, a very important one that can often be overlooked, well, all those things we didn't include it, because we can never boil the ocean and include everything. We have to accept or assume, qualify the answer by stating that we believe none of those factors we didn't include or we didn't quantify the uncertainty for actually affected the outcome. They were inconsequential. So the verification and validation in this context then has to be to set out a data collection plan to say, okay, how do we test these things, confirm that all of these assumptions were appropriate and proven to be right. So it's about sort of completing this loop. So hopefully you can read the key there. So we've got essentially predicted population means and standard deviations, and then means and standard deviations. So that's where we're starting off in the process as described on the previous slide. We have assumptions for population parameters that we use as inputs to our process. We model the effects of variation through our UQ technique, and that obviously gives us predictions for the population parameters of performance characteristics or behaviours. Then we have to, as I say, plan to collect data, real-world data, which obviously is sample data. So sample data in terms of conformance, mean, standard deviations of those same performance characteristics, and the same for the inputs. Obviously, we have to develop these over time, so we might start off with what we call short-term views, but ultimately want to build that data up to long-term. As we progress, we will become more and more precise in our estimates of whether we are actually right in our assumptions or they're proving to be wrong. But we have to, again, plan for that evolution of terms, shall we say. And then, as I say, the comparison, the verification and validation part is the comparison of those two sets. So are those real-world samples aligned to the parameters of our predicted performance? Are those real-world samples of the inputs aligned to our assumptions? So if we can answer yes to both of those, then what we've got is a verified and validated system. If it's no to one or the other, then clearly we need to understand, well, if it's because we made the wrong assumptions, if we update those, hopefully that corrects the situation. If the assumptions are right but the predictions are wrong, then clearly there was an issue with the model itself. So that's sort of the long and short of it, as it were. Hopefully that's made some sense. As I said, what I just want to leave you with here is something that makes you think, like, well, actually, okay, we can verify and validate all these complex models, but,
Can you hear me over this microphone also?
Yes, I can hear you.
All right. Well, yeah, thank you for this talk, Gordon. I think it was a very nice overview over the validation and verification of models in the light of using models and doing robust design and seeing the world as something non-deterministic. Thank again. I think we have time for a couple of questions. Anything from the audience? No? Well, then I'm just going to start out. From my experience also working in that industry, I thought always it's pretty difficult to actually reflect all these stochastic things in the testing, because you have just a limited amount of engine builds, and usually you test very different things with very different mods, so that you can actually not really see the natural variation. Do you have some comments on that?
Yes, yeah. I mean, it's a very frequent question asked typically from the chief engineers of a program to say, well, okay, all this statistics is very good, but can you give me the statistical test when I have a sample of one? To which the short answer is no, because there ain't no such animal. But I think obviously what you have to do in those situations is either, a single engine that's part of the development program is really a platform for a series of tests. So you can plan those either through design experiments or other techniques, but again, systemically identify, well, what are we trying to discover? Maybe it has to be just a series of repeated measurements or a series of trials or runs of that engine to give you some sample. Obviously, it can't therefore account for all sources of variation, but at least you have information on some things. It's typically important, of course, when you're making a deliberate change to engine to show an improvement. So, you have to, it now becomes a two-sample test. Is the average performance before better than the average, worse than the average performance after the mod? So even just thinking in those terms can be difficult, because it's always, we only want to run it once. I think more widely, you can think of the whole engine development program as a series of varying tests where there are potentially these special causes at play where you have made deliberate changes, and treating the analysis of the development program as a whole, as a sample with expected changes in means or variations is another possible approach.
All right, any more burning questions from the floor? Well, thank you very much for linking in, and I'm happy that it worked out quite well, actually. Thanks.